Well, let's get into chapter 15 then. Thanks again, Chris. I know they appreciated it.
Sure. Thank you, guys. Appreciate it.
So I'll start this. How's everybody doing? Are you glad that we only have a few weeks left? It's already November. Oh, let me see.
Yeah.
I lost my share screen button. Where did it go? I don't know if I'll ever find it with this thing on. I think I put you guys behind the presentation, which means I can't get there. Yeah, that's what happened. So I'm gonna move you guys over here. Try this again. Okay, great. Looks like I've got everything organized now, and you can see it. I'm caught up on the chat. Thanks everybody for your support of Chris there. He did a good job. So we're looking now at chapter 15, one more left. After this, there will be a quiz next week on chapter 15. I'll try to get Chris's presentation up quickly because we might want to pull one of our questions from there too. Let's keep going though. So, when I look at this chapter and I look at where we are and some of the things it's trying to teach, I think you're going to react and say, look at that computer in that figure. That thing is, 20 years old or whatever. It's not relevant to me anymore. Am I right? Is that what you're thinking when you see this? Nobody wants to be brave.
Yeah. Old computers, too much room. They take too much room.
Right. So what I want to ask you to do, hopefully you've all read the chapter, but if you haven't, go ahead and read it. There are some things in the chapter that do show their age, but the fundamentals are still true. And that's the point. That's the whole point of your undergraduate degree, is to get the fundamentals right. Because when you do, they will never change. And you can use those and build on those, just like Chris was saying. When you see something, you're going to build this engineering intuition for how to reduce stress in a part if that's your responsibility, for example. So whether or not we see antiquated monitors and computers in this image, the point still remains true. There's a design function, a scheduling function, a planning function, a control function, all of which could be automated, which is what we're trying to show here. Computer integrated manufacturing is really automated manufacturing is done through this. And then there's all the things that can happen on any kind of manufacturing floor, whether it's one with a CNC, an assembly, or whatever it might be. We've talked about injection molding or thermoforming, whatever it might be that goes along here. You have the parts that are coming in, whatever you do to them to change them, finish them off, maybe measure them, and then what do you do with them? How do you get them out of here and send them to the customer? Because that's really where the money is. And maybe it's not some robot that looks like this, but some other robots in your factory that allows this to happen. So the fundamentals, like I said, have not changed. And we can simply be more efficient if we take less space and use modern tools to execute these established systems. So here we go. We just talked about CAD, and we talked about making simple parts like that triangular part. Here's a more rectangular part with a circle through it. You should have already taken some classes that talk about modeling and drafting and the way you can draw these up. This is just reminding you of ways to think about them. They might be intuitive to you already, to be able to see a side view and a top view and understand what those lines mean. But they're not intuitive to everybody. This is reminding me, in the case of design patents, you can hand an attorney that's going to make that patent for you a wire drawing like this, and he might draw something or she might draw something that would not look like the real part. And if you ever take that patent to court to have it defended, if you don't have those lines there, they're going to say, that's not your part on the design patent. So, it's not intuitive necessarily. Are there questions about these kinds of 2.5D, 3D? Most of you are probably playing with CAD software already. Are there any questions about this topic? Just as one more layer of information, we're going to get a little bit in the book about parametric design and the different types of files that are out there. If you can come up with something that's easy for the machine to remember and easy for your machining system to produce, it might be a layered structure like this, say for 3D printing, for example, that you have to break your 3D part into. So we'll talk a little bit about that. But what do? In reality, you have to represent space, and you're only able to assign points in this cloud, this point cloud. And so how do you interpret or interpolate between those points? Well, the book gives you a few options. They talk about these Bezier curves or splines that you can use, and some of the advantages and disadvantages of these options. In the case of this curve, one of the points that they make in the book is you make some small change here, and as a more global effect to the rest of the curve, you see implications of the dashed line here changing far from where you made the dimensional change. Whereas if you use more of a spline technique, you still see some deviation far from this change here. If you look here, but it's minor compared to no change. If you get enough neighbors away, here you are, you're at the change. So this is U 0. Here's first neighbor 1, second neighbor 2. Everything's already okay. Same thing here. First neighbor 1, a little bit of deviation. Second neighbor 2, and by now everything's probably okay. So this is what you're thinking about when you're selecting an integrating or averaging technique for representing space by points, when in reality space is not even a line, right? Artists, I have a whole book somebody sent me, I think it was a week ago, that online, that I was surprised how many, it was like almost a gigabyte for this book, because it was an art book showing how lines are defined by artists, and they're not lines, it's edges, and even edges are fuzzy. And so how they handle it, how machines handle it, this is all an area of research, not just in engineering, but also in art. So we also have not just lines, but solids that we need to represent. We can enclose surfaces. We can think about the meshing of those, and it can be a combination of primitive shapes like cylinders, cubes, flat cubes or plates to build our model. And then it can be parametric equations that define those shapes. And if you look here, this is an STL part, and you're probably already familiar with STL files. Really became popular and then became the standard for a lot of file transfer, even between non-stereolithography parts, simply because stereolithography was popular around the time computer file saving was and exchanging needed to happen. Then just legacy brought it down to us to be used even for 3D printing and other non-native STL parts. And it's the same concept Chris was talking to you about, where if you're too coarse with your mesh, or with, you can also call these elements, because it's finite element modeling. You're too coarse with your element, and distance between the nodes, you'll miss the shape of the ideal surface. Now you can get some of that back if we go back a slide or two. You can get some of that back with the right interpolation in your machine code, but the representation will be a little bit off. Jamin, I'm curious if this is sort of old stuff to you, or we deal with this every day.
Sort of, not really. I actually took some of the and I think it's kind of a shame, but I took some of the engineering tech classes at TCC because I got scared of calculus, and so I started splitting my time between them. But I don't think the regular mechanical engineering program really goes into as much of this kind of stuff as the engineering tech one does. Like we never took a GD&T class or anything like that unless you take it in the tech program, which I think is kind of a shame.
Yeah, I've heard that before from other students. You'll have to get the 40,000-foot view when you're done to see why that is. But, it's good to learn as much as you can.
Yeah.
So I'm not against it. I'm not against it doing both. So here's that parametric design that I was talking to you about a minute ago. And it feels like we've talked about this in one other chapter before. Maybe it was more about designing for robustness. But, if the goal here was to kind of reduce some waste by bringing this outside radius down, then all you have to do is look at the relative position of these parts, and you can do that. Now this was obviously longer too, so they made some other changes, but they're able to just assign this numerical change, and by having relationships between, this is the center, this is the center from the top, this is the center from the edge, etc., then you're able to make a small change in your CAD and make a significant change in the part without having to step through a whole bunch of elements or something. Speaking of elements, that mesh refining exercise that Chris was talking to you about can kind of be represented here when we talk about this octree representation of a solid object. So, how am I going to represent this this triangle within the square? Well, the square is bigger than the triangle. So you divide it once and you say, well, I don't need any information here, but I still have these three places covered. And you just keep dividing until you get enough information to determine the edge, in this case, for the triangle. And you can see you have most refinement around where the change is most abrupt, which is, these corners and the ends, and then you can deal with larger squares here on the interior. In fact, you don't really need these four. You could make that also larger. You can do the same kind of thing for more complex objects. You just come up with a skeleton data structure for those objects. Here the dash line is representing to you for some simple ones, and then you can imagine a more complicated object can be simplified with a skeleton model for at least the important parts that you want to model. Now keep in mind this is referenced from a 2012 source, so we certainly are much more complicated now, but as I said before, the fundamentals are the same. So do any of you guys use routing sheets in your real lives?
Yep.
I figured that was the case. And, maybe something that's not surprising is that you see the inspection at the end. You see a little bit of inspection in the beginning, and then the processes that need to occur as it's passed along. And there might even be an inspection at each step. It just kind of depends how complicated it is, how obvious it is. But I see these today, even though, like I said, we're talking about things that are maybe changing quickly. It's in use all over the world. I've seen I've been to machine shops in multiple countries this year that are using routing sheets. Maybe one of the new things that's going on is to use RFID tags to go with the cards and try to reduce the amount of operator error in typing things in. You can scan barcodes, this kind of thing. Well, it's going on now. Grouping parts according to their geometric similarities is important. It helps add a little bit of efficiency to the batch style of manufacturing, which is pretty common still today. I think it'll never go away because we'll always need small scale, flexible manufacturing centers. But obviously costs go down if you can scale beyond batch. This we have a couple of parts up here, and the comparison is, are you going to do 10 parts per month, or are you going to do 10,000 parts per month? And how to set those up in your system will matter. And then if you're doing this, not so different parts, you can run those without having to say change your adapters in your fixtures. You can use the same set of adapters on your lathe, for example, and run these parts. So let's see, functional layout of machine tools in traditional plants. Arrows indicate the flow of material and parts in various stages of completion. There's this group technology concept here. We have lathe, milling, drilling happening in groups versus, a part is received and the operations then need to be done in a certain order, where you might go from lathe, mill, drill, grinder here. And then I think there's a good example of they still kind of have them in sequence. But I think you might find some where you have lathe, mill, and lathe again. But I don't see it here. So we have a decision tree classification for the sheet metal bracket, really similar to some of the stuff that Chase showed you before. We see, the processes that need to be done in sequence. And so we have this work here that's going on in sequence. And obviously you want to do the holes, for example, after the bends. You want to get them in the right place. Let's go to the next slide. Classification and coding scheme using the OPIT system. So we have 5 digits and supplementary code for 4 digits, and there's some other coding systems too, shown in the book. I don't know that you guys are familiar with these, but it's again a way to assign parts and shapes that is, from my perspective, not used as often, but there might be a few of you that are exposed to this. If you look at the next one, it's more of a code classification for a machine part. Again, you don't have to memorize these. The machine can read that for these computerized systems. And I've seen people actually get away from this too and to go to something that's completely agnostic to what the information is. It's just a code that is used to keep parts in sequence and not confuse different SKUs. Here's the KK3 system for rotational components. He says a little bit about this in the text as well. Certainly the surface properties really matter, and you want to watch out for that. That's where I've seen kind of mistakes made in machining in the past. It's kind of hard to get the wrong major dimensions out the door. You'll see that you've done that wrong, but it might be easy to get the wrong surface treatment out the door for something you're producing. Use of group technology, they call it, to organize manufacturing cells. There's several kinds of those discussed in the text as well. And what I like about this, the part that I personally became involved in, is where we can make the groups larger. and more encompassing. And the term for that is vertical integration. So you take what were independent subgroups and bring them together and make that a larger independent group. And the same thing that they talk about in the text about the freedom and autonomy of the group to kind of make its own decisions and be efficient with its own system, you can become even more efficient. So this is the hint I'm giving you for wherever you might go to be an engineer, say next year after you're an alumni of OSU. If you can help that company vertically integrate, you're likely going to help that company reduce costs and increase profit, because it's the exchange between these independent groups where you lose some of the value that you would get after you vertically integrate. Any questions about that? So here's an example of a complete cell that has all the operations in one room. So you're not, packaging it up and selling it to somebody else to do the finishing. You do all this in-house. Just again, because it's a little bit of an older reference, we have the humans here indicated by these cylinders. But these are the stages in the process as you go around this room from clockwise, from raw material to a finished part. Here's another schematic, and this is, I think, one of the last 3 or 4 in the text. So we're almost done with the chapter now, and we have this automated guided vehicle, AGV, that's passing the material around. I think it was with you that we talked about those when we saw the aluminum manufacturing facility. And I mentioned how some of these are so well automated and so precise that you'll actually see the ruts, not engineered by the wheels in the floor, but because everything's doing the same thing all the time. But again, the more automated you get, it's just better for consistency in the parts you make, which then leads to, I highlighted it in your text. It's right at the beginning. I'll read it to you here. It says, marketing poor quality products can indeed be very costly to the manufacturer. And it really comes down to quality. So the more consistent you can be, the better quality you can have. And even if you're consistently making a part incorrectly, if you know how to be consistent, then you can move that parameter that was incorrect into the correct space for your customer. So it really is important to think about it this way and see what you can do. I'm so inclined to help you with this that if you run into the problem after you've left OSU, come back to me and let me help you, because it's going to make a difference for our economy. Let's see. A general view of a flexible manufacturing system. This is, again, a little bit of an older photo, but there's this battle between flexibility and scalability and margin. But this one's pretty good, but you can imagine how heavy these machines are. The flexible part is the tools and adapters that go within them. The less flexible part is actually moving the equipment around. But this is, again, something I see all the time, pretty typical. You have nice reinforced cranes that you can typically move between machines to move molds around or move the tools around. And then you are passing completed parts along this conveying system here from one station to the next. Here's the characteristics of transfer lines and flexible manufacturing systems. So the transfer line, generally few parts. The flexible manufacturing system, it says infinite but many. Your lot sizes for transfers are larger, flexible or less. Then you've got your part changing time, your tool changing time, adaptive control, inventory. You have to keep a larger inventory for the transfer line. That gets into just in time, which I think is one of the next slides. Production during breakdown. With the flexible system, you can still make parts. You've got one of your drill presses down or something. Your efficiency, though, will never be as high. in the flexible system. Now, why is that 60 to 70? I disagree with that. We'll need to look into the text on that one. And justification for capital expenditure is a little bit more difficult with the flexible system. Here we have 3 basic types of topology for a local area network. All of this is history almost. It's kind of well known, taken care of. Why is it in this text here? Well, because we have to put it somewhere when we're talking about networks and eventually computer systems, so it sits here. It's useful though, because even I, in my early engineering career, was dealing with antiquated systems that need to be updated. So having some awareness of how people used to do things is still useful, because you don't know what kind of companies might get purchased and become part of your new company that has old technology. How can you use it? How do you replace it? It's useful to be aware of. Use of cloud computing. This is newer. This is well known now. Evolves a lot, even over a few months now. But this is where the future is. I talk to leaders in manufacturing today that are, flying out to Amazon and flying out to Oracle and all these different places to get involved in the future of cloud computing, artificial intelligence, etc. And we can connect all of our tools to these systems to better automate, improve quality, which then improves our margins, because our customers are happier. The basic structure then of an expert system is discussed in your book. You might have a natural language interface. This is obviously becoming more common, whatever the control structure is, and then the knowledge base and databases that are formed from the input data. So what they sort of mention in the text, but it's not as well documented here, is the role of artificial intelligence in this, or better yet, large language learning models. And we can still talk about that if you guys want to. So the one area that people forget is that AI has been around a long time. One of the areas that it was kind of obvious, or maybe more immediate to integrate it into, was machine vision. And here we have a 2-camera system demonstrated for an object that is manipulated by a robot. And you might, for example, be planning to machine that part, orient that part, etc. with this machine vision system.